All right. Good morning or good afternoon, everyone. Here we are to watch video 4.8, where we are going to learn about the big four equations. Now, I'm actually stealing this video from Mr. Boltrey. He does a good job of explaining the equations and where they come from. And once we've learned those equations, we've gotten them written down, we're going to go through a couple practice problems on the board that are located on your classroom. Okay, so make sure that as we're watching this video, I'm going to pause and add a few things on my end, but make sure you're going through taking notes and making sure you're getting everything from this written down, okay?
So first, we're going to introduce the equations, talk about what they are and why they're important, and then I'm going to walk through each one at a time and show you where it came from. Because I believe it's important to, if you're going to use an equation, to know at least where it came from. So first, before we dive into any of this, there is a huge rule before you use any of these big four equations of constant acceleration motion. And that rule is that in order to use the equation, this condition must be met. The object must be experiencing a single constant acceleration. If it is a changing acceleration or more than one constant acceleration, like it's one at the beginning and one at the second half of the problem, you cannot use these equations. You have to use a different method or split it into half and solve those two constant accelerations separately. But this rule has to be met in order for you to use these equations. So here are the big four equations. At this point, you might want to pause and copy down the equations. We will talk about what each of them is and what they mean and what they're doing one at a time. But I just wanted to start right up front by showing you what the big four equations of constant acceleration motion are. And so also I wanted to talk just briefly about why are equations useful in general. So up until this point, we've been solving everything graphically, and graphically is a really good way to solve problems. For example, if I were to give you this problem, a car accelerates from 10 meters per second to 15 meters per second over the course of 8 seconds, how far did it travel? If you were to use a graphical approach, how would you solve this? Well, first you'd have to get your graph paper, you have to get your VT graph, you would do 10 meters per second to 15 meters per second. And then we know displacement is the area of a VT graph. So you have to find the area of this trapezoid, maybe by splitting it into a rectangle and a triangle. And then you would know the displacement, which that was probably like 4 or 5 or maybe even 6 steps. And it maybe took you 4 or 5 or maybe even 10 minutes to do all of that. Whereas if we have these equations, which are basically doing the same thing, just in a more systematic, easy to use format, we can just pick the right equation, substitute in the variables, and then have our answer in a 2-step process that takes 2 minutes. So that's why equations are useful. It allows us to do the things that we've already been doing graphically, just a little bit faster, a little bit easier, a little bit more convenient. So that's why the equations are useful. But then the next question is, well, why are there 4 equations? Why can't, that's a lot to remember. Thankfully, you can just write them down in your lab notebook. You don't have to memorize them, but still, that's a lot to work with. And the reason why there are 4 is if we think about the kind of things that I could give you in a constant acceleration problem. I might give you the change in position, a change in velocity, an acceleration, change in time. And you'll notice that change in velocity is mostly in the initial velocity and the final velocity. So with these 5 variables in a constant acceleration problem. Let's say that I gave you a problem and I didn't give you any information about the change in position. But I asked you, let's say I gave you the initial velocity, the final velocity, the acceleration. I asked you to find the change in time. Well, you're going to look over here and, well, which equation do we use? If we don't have any information about change in position, we're going to grab the equation that doesn't have change in position in it, because that's going to allow us to solve for the other variable. Assuming that we know final velocity, initial velocity, acceleration, we can just do some algebra and solve for change in time. Let's do another example. Let's say I give you a problem and I don't give you final velocity, but I give you the other information. Well, we're going to go and we're going to look, well, this equation has final velocity in it, so I can't use that one. So does this one, and so does this one. So I'm going to be left using this second equation. And then given enough information, I can solve for the other variables. Let's say I gave you change in position, the initial velocity, and the acceleration. You could, again, use algebra to solve for the change in time. So hopefully you're seeing the pattern at this point. If I don't give you acceleration, you can use this third formula to solve for the other variables. And if I don't give you change in time, you can use this 4th formula to solve for the other variables. So to put it a different way, since there are 5 variables involved in constant acceleration problems, we need 4 equations so that if I give you 3 pieces of information, you can solve for any of the other 2 unknowns. So that's why there are 4 equations for constant acceleration. So now we have the equations written down. And like I said earlier, if you're going to use an equation, you have to know where it came from. At least you don't have to be able to derive it on a quiz or a test, but you have to have some understanding of where did this equation come from. It wasn't just made up out of nowhere. So the first one is the first equation that we showed you, and that's going to come from a velocity versus time graph. Remember, how do we define acceleration? We said it was the slope of a velocity versus time graph. And
really quickly, y'all, you do not need to write the derivations down in your notebook. However, I do want you to see where these equations are coming from. Like Mr. Boltre said, we want to know why these equations are useful and know that they are valid in terms of using them for physics problems. So again, you don't need to write these down. If you would like to, that's great. We just want to show you and have you be able to explain where these equations come from, okay?
Since slope is rise over run, that's going to be change in velocity over change in time. Well, remember, change is final minus initial. So I can say acceleration is final velocity minus the initial velocity divided by the change in time. Then I can just do some algebra rearrangement, multiply both sides by delta t, and then add VF to both sides. And then this equation is the same as this equation, just with some algebra rearrangement. So this one just came from the definition of acceleration as the slope of a velocity versus time graph, rise over run. And don't forget the huge rule: in order to use any of these equations, it must be experiencing a single constant acceleration. Let's skip around a little bit and move to the third equation, because this one is kind of easy to understand where it came from. So delta P is another word for displacement or change in position. And we're going to go again back to our velocity versus time graph. Where do we see displacement on a velocity versus time graph? Hopefully you remember that it's the area between the velocity function and the horizontal axis. So in this situation, this is going to make sort of a trapezoidal shape. So you might have to go in your geometry textbook or just Google, what is the area for a trapezoid? And it's 1/2 times the sum of the bases times the height. Now remember, this is a trapezoid that's sort of on its side because the two bases are the two sides that are parallel, and the height is the this side right here. So in this situation, if we substitute in our variables, my two bases are the initial velocity and the final velocity, and the height is the change in time. So you'll notice that that's how we get the equation: 1/2 times the initial velocity plus the final velocity times the change in time. And this just comes from the definition of displacement as the area of a velocity versus time graph using the area of a trapezoid formula. And don't forget the huge rule as always. Let's go back to equation number 2 because it's very similar to the equation number 1. You'll see we're still solving for displacement, which is still going to be the area of a velocity versus time graph. But if you do forget the equation formula for a trapezoid, you can break this trapezoid into a rectangle and a triangle. The area for a rectangle is base times height, or length times width, which the length of this is the change in time, and the width is the initial velocity, which is where we get the initial velocity times the change in time from. And the area of a triangle is 1/2 times the base, the change in time, the change in time, times the height, which is the change in velocity. So this formula is very similar to our original formula, except remember this one was important because we didn't need any information about final velocity. So this delta V is a little bit pesky there. We're actually going to replace it with, remember, this is the slope of a VT graph, is acceleration. So we can say that delta V equals A times delta T. Then we can just do a little variable substitution. And where we have a delta V here, we can put in an A times delta T. So then we'll get 1/2 times A times delta T, which is just 1/2 times A times delta T squared. And there we have another equation, another way to solve for the displacement. But this time you can do it without any information about final velocity. As always, don't forget the huge rule. And this last equation is the hardest to derive. It's the most sort of mathematically complicated. So I don't want to do every single step, but let's take the first equation and the third equation. And remember, the whole point of this last equation is that it has nowhere in it any information about change in time. So what we can do is we can algebra rearrange this first equation to solve for change in time. I just move some stuff around using algebra to solve for change in time. And then what I can do is I can take this delta t, and anywhere I see a delta t, for example, over here, I can do a variable substitution. So instead of delta t, I'm going to have a VF minus VI divided by A. So the equation will look like this. So I know it doesn't look the same, but this equation is actually exactly identical to this equation, just with some algebra rearrangement. And I totally encourage you to check my math on that. The most important thing is don't forget to double distribute. So make sure you multiply the first by the first, the last by the last, the outside and the inside, double distribute and then simplify, and you should get this equation. So that was a little bit complicated, but the most important thing to remember is that we just solved for one of the equations in terms of delta t and then substituted it into another equation. And why did we do that? So that we would have a final fourth equation that didn't have change in time anywhere in that equation. And then we just did some algebra simplification to make it look a little bit easier and ended up with our fourth equation. So long story short, this is where the four equations came from.
I'm going to skip through this because we just talked about it with the derivations. Okay, so a couple things from me, right? Thank you, Mr. Boltry. You did a wonderful job. A couple things from me when it comes to constant acceleration equations, right? We're going to work through a couple problems, but there are two things I want you to write down here. And that is that whenever a problem says that an object is dropped or it starts at rest, the initial velocity is going to equal 0 meters per second. Okay, because if you imagine us just dropping an object, we're not throwing it, so we're not giving it an initial velocity, we are simply dropping it. So anytime we say dropped or starts at rest, it means that the initial velocity is 0. And just like we found out in our falling objects lab, if an object is falling, the acceleration is going to equal that acceleration due to gravity, which is -10 meters per second squared. So anytime we have an object that is just in free fall, that acceleration is going to equal -10. Okay, so let's go ahead and flip to our first problem in that classwork assignment that we've given you. Okay, and it reads like this. In our marble down a ramp lab, you had a marble that traveled 1.1 meters in 5.5 seconds after starting at rest. What was the acceleration of the marble as it rolled down the ramp? So the way I like to solve these is I write out every possible variable that I can find, and I just want to pick those values out from the problem. So for example, our initial velocity. Well, like we just noted over there in the purple, the initial velocity is stated right here. It says we're starting at rest. So our initial velocity is going to equal 0 meters per second. Our final velocity, I don't know, does it say it anywhere in this problem? It does not. So we don't have final velocity. Our acceleration is what we're looking for. What was the acceleration of the marble? So I'm just going to put a question mark right there for acceleration. Change in time, it says right here that it took 5.5 seconds to travel down the ramp. So delta t is going to equal 5.5 seconds. And then our displacement of delta x is listed right here, right, at 1.1 meters. So 1.1 meters, right? And so these problems are only using the first two equations, which is VF equals VI plus A times delta T, and delta X equals VI delta T plus 1/2 A delta T squared. So if you remember, we don't have the final velocity for this problem. It's not given to us and we're not looking for it. So to determine which equation we should use, we need the one that doesn't have final velocity. Well, this one does, and this one doesn't. So we're actually going to use the second equation to solve this problem. So let's write that out. We're going to have delta x equals VI delta t plus 1/2 A delta t squared. And then we're just going to substitute in the values we have. Delta x was 1.1. VI is given as 0. Delta t is 5.5. 1/2. We're still looking for the acceleration. And then our delta t, like we said earlier, was 5.5 squared, right? And we can do that math, right? And so this would go away. We would have 1.1 equals 1/2 times A times 5.5 squared. I actually don't know that off the top of my head, but what we can do is we know that we're going to move everything from this side over to here, right? And so you would do this math, and then whatever you get, you would divide both sides by that value, and you would get your acceleration answer, okay? So then quickly moving on to number 2, let's say we have some, oh, sorry. So you have the problem on your sheet. I kind of cut off the first part, but it says, let's say they have some starting velocity, and then they accelerate at 1.5 meters per second squared for 8 seconds to get to a final velocity of 42 meters per second. How fast were they going before they sped up? So what does this problem give us? Well, it says the acceleration right here is 1.5 meters per second squared. It says that the time is 8 seconds. And it says that our final velocity was 42 meters per second. Final velocity of 42 meters per second. So we have 42 meters per second, and we are looking for our initial velocity, which means we don't have our displacement. Our displacement is going to be in this problem, so we need to use that first equation in order to solve this. And I trust that you all can put those values into the equation and do the math yourselves. So that's a little demonstration on how to use constant acceleration equations to solve problems. Obviously, I am not here, but if you have any questions, feel free to email me or to see Mr. Alleman after school and tutorial. I hope you all have a wonderful day. And as always, go Bears.